Hello everybody, welcome to lecture 4 of CS224D. Today I think is very exciting because we're going to start introducing the last very basic Lego block, and then starting next week we'll actually get to really interesting juicy bits of deep learning that will then kind of fulfill the most basic Lego blocks, and from there on we can play with much more higher level kinds of models and ideas, and it'll be very exciting. So today we'll basically finish up some general classification background just to refresh some of the ideas from 229 that you may have already seen. Then look very carefully at updating word vectors, what happens to them sort of on an abstract level. And then we'll get to the first model that will actually be useful for downstream tasks, which is a window classification model. Very simple. We're going to classify single words, but in their context. And then we'll probably just get to defining the first and major Lego block, which is a single layer neural network. And then next week we'll get to how to actually train that. And then after that it'll be sort of much faster in pace because we have all the basic tools to really start building interesting models and putting all these tools together in new ways. Are there any organizational questions so far? You should have seen problem set 1, had a first look. Yeah?
Up to what lecture would we be given with all the material to do the problem set?
You should be able to do the problem set already, most of it. Yeah. So you can get started on it right away. We try to time the lectures usually in a way such that once the problem set comes out, you should be able to get started on it.
But the problem set has many neural network related questions, and we are only doing neural network now, right? So
that's true, but you can already get started because some parts of it only require word vector learning, and those you can already get started with, and then the second part of the problem set is something you'll learn about today and next week. Yeah.
Do we know when the midterm is going to be?
That's a great question. I think we have a date. There's only 1 week in which it can be, and then we only have these 2 Tuesday, Thursday classes. I want to say, David, do you know if it's on the website? All right. Maybe we'll follow up at the end of the class. Good question. Cool. All right. Let's get started. Classification, some setup and notation before we can get into what it's really about. So basically, in general, for classification, we usually assume we have some kind of training data set where we have some inputs xi and some class yi. And we usually have 1 to n many samples. Now, xi for our purposes will usually be either the words, could also be the entire context window of multiple words, could be whole sentences or even entire documents. And we'll usually try to define that properly when we actually look at each problem separately. Yi, in most of our cases, will be just simple labels, but it could also be entire other words. Words and labels will be in many ways treated very similarly, but of course, labels you usually have only a handful or a dozen, whereas if you try to predict a bunch of potential words as output, where each class, so to say, is predicting whether that word is the next word that should come in a translated sentence, for instance, the output space is much, much larger, and then we want to be very careful about how we treat the softmax classification, for instance. We'll get to that in a bit in this lecture. The class could just be sentiment, so for most purposes, you can simply think of yi as one of the potential classes, like very negative, negative, neutral, positive, or very positive, one of 5 classes. Named entities are other ones that we'll see a lot in this class, but it could be very high-level things too, such as buy-sell decision based on reading some article or something like that. So pretty high level. And we'll later in this class get to multi-word sequences where the output space is actually not just a single label, but a sequence of output labels, such as a sequence of words that we want to translate a sentence into. So let's look at a little bit of the intuition for the classification. Let's say here we'll have a very simple 2D problem. Let's assume, for instance, these 2D points are all word vectors. Word vectors that are simply 2-dimensional. again, rarely ever will we have a real example where it's in 2D. This is just for illustration. This is actually a great visualization from Andrei Karpathy that I encourage you all to play around with. This is not a confident, this is just a simple logistic regression model, hence with no extra features added, you would just have a linear decision boundary to try to separate out these 2 points. But it gives you great intuition if you play around with this demo. So the link is in the slides, and I encourage you all to play around a little bit with it and see how eventually we're going to add different layers, and you add new points to your training data, and it changes the decision boundary. It's very intuitive. So let's say we have this simple classification problem here. We have green points, we have red points, and we have a linear decision boundary. And let's assume for now that x is fixed. So the word vectors may be fixed. They may have come from glove or word to vec initialization, but now we just try to classify each word separately and independently. So in this case, we would only train our logistic regression weights W here to modify where exactly that boundary should be. And this is again our definition of softmax, or the softmax classifier, or the logistic regression classifier. We're basically just for each probability, to compute each probability of a class Y, we'll basically have the exponent and the inner product here of the ith row of W times the vector x. And we normalize this by summing over all the inner products with the other classes, with all the classes. All right, now we introduced in the last class the cross-entropy loss function over a specific data set. So let's use our notation here. Let's assume xi is our data input x, and we have the class yi that we'd like to predict. So then we're going to basically sum over this expression here the negative log of basically here our exponents, where fyi is just that inner product that we defined in the slide before. All right, now usually what we will do, and this is going to be an important, one of the most important takeaway messages for this class, is how to write these kinds of operations in matrix notation, because matrix notation will enable you to implement this much more efficiently in code, and we'll look at some code examples and timings specifically in this lecture. So instead of saying we compute this actually by taking out a specific row in our W matrix and then multiplying this with x, of course what we'll instead do is we'll compute the entire vector of features f of the softmax with one large matrix multiplication, right? And each row is essentially independent, and hence we can parallelize this computation very well. Any questions so far around the notation? Yeah.
I was just curious, why do we use cross-entropy loss as opposed to some other loss function like mean squared?
It's a great question. So why do we use cross-entropy loss versus mean squared error or max margin loss and so on? We will actually use the max margin loss function a lot in the future. This is kind of the most basic one. It's very well understood, very common. It is still used very frequently. As soon as you have a lot of classes, or you want to speed up your training, or you don't care exactly about getting probabilities, you will end up using the max margin loss or objective functions much more frequently. It turns out squared error does not work very well with neural networks, and it's still not very clear why. There's no nice theory of why it doesn't work, but in most cases squared error loss will not give you great results. So this is a little bit outside the scope of this lecture, so don't worry if you don't understand it. But generally, well, this specific lecture, maybe eventually for your projects, you might want to keep this in mind. But when you try to even predict a real number, you would usually want to use a kind of linear regression output and a squared error loss. But even then, it's better to make it into a classification error and then have a weighted sum of your different buckets of numbers to predict the final output. It just happens to work much better in practice. It seems like neural networks have and that's just my intuition, I don't really have a great backup for this, but they have very sort of high volatility dynamics, and so they can be very clear about it's this class, but if you kind of overfit to specific numbers, they're just not very stable. But yeah, great question. We'll look at other objective functions, and I think even the next week. All right, now whenever I say we use the cross-entropy error, I'm kind of lying, and really what we always use is a regularized version of any error. So throughout the lecture, when I focus on different kinds of loss functions, you can almost always assume that we also have our regularization term here, where we essentially assume we have a Gaussian prior on all our weights, all our parameters of our model, and we'll try to keep those to be close to 0 if we can. And we're going to penalize in a square term here any deviation from 0 for all our parameters. Otherwise, we'll always overfit these very powerful models. Yeah?
Yeah, I just wanted to ask on the previous slide, so we're talking about x as d-dimensional, so that would correspond to like one word, I guess. Wouldn't the number of features get out of hand once you have?
That's a very good question. We'll, in fact, talk about this right here. You're right. X will be our d-dimensional word vectors, for instance, often, and we have a lot of word vectors. That's a lot of parameters, and so you'll very likely overfit. And if you want to train your word vectors, you better have a very large supervised training data set. Otherwise, it will overfit very quickly. And we'll cover throughout this class a lot of techniques on preventing overfitting. In fact, some could say that a lot of the techniques in deep learning have been around for 20, 30 years, but it's really now that we understand, one, that if you have enough data, the data by itself almost regularizes your model. And we have various techniques, which we'll cover in this class, such as dropout, or now even stochastic depth networks, where you have variable numbers of layers and so on. There are lots of different techniques, sparsity constraints and so on, that we'll cover in this class in the upcoming weeks to try to regularize these models better and better. And in fact, sometimes you might not want to update the word vectors at all. We'll get to that in a bit in this class. In today's lecture. So basically, this regularization term will help us prevent overfitting, and this is one of the most important graphs that you may see in any machine learning class. In fact, when I took my very first machine learning class, the professor said this is the most important graph in machine learning. Basically, the x-axis, and it's by design here that I didn't write a specific one, it's essentially the model power, or the number of parameters, or the amount of training time that you have, and things like that. So basically, things that make your model more powerful and more accurate. And then on the y-axis here, you basically have your error. And in blue, you have your training error. And as you add more and more parameters, for instance, your word vectors, that's the one thing we now know already. If you make your word vectors 500 dimensional, and now you train them, your training error will go further and further down. But at some point, your test error will actually start increasing again. And so in all the cases, what you will want to do is first have a proper train and test split of your data set. In fact, what you really want to have, and we'll get to that in future lectures again also, is a train, development, and test split. And you're going to want to compute this graph on your development split. Basically, you just take your inputs here, and you take, for instance, 80% of your data points for training, 10% to develop and test and basically visualize a graph like this, and then the final 10% you only run once a week or once a month in a real project to understand how well your data would actually work on held out data sets, or on held out data in real life. All right, so this term is the simplest way we can prevent overfitting, but it certainly is not the only way we'll prevent overfitting. All right, so now for general machine learning, our theta will in most cases just be basically the columns or rows of W. And here I will introduce the opposite of the rows. Whenever we see dot and then the index, then that means we'll take this column of the data set. So here, just to get one long column vector, we take all the columns of W and we define this W here as basically our entire theta. That's the standard for machine learning, where we used to always have specific hand designed features, and we just want to weight those features to make a final prediction of a class. So in this case here, we would have C, the number of classes, times D, the input dimensionality, many parameters in the model. And that's the only thing we would update when we update our model. And we compute the gradients, and we plug that into stochastic gradient descent method to update our theta. And in this case here, all we would do is basically update this decision boundary. Now, in deep learning, we want to try to do end-to-end learning. So anything that can be learned, we try to learn. In the case of NLP, we at least have a word index, but then the word vectors are ideally part of the training model and part of what we already update. And so what we'll more commonly see is that we have both W, the softmax or the logistic regression weights, as well as the word vectors. And that now, of course, increases, and you already pointed this out, the number of parameters by a lot. Because V, again, is the size of our vocabulary, and D is the dimensionality of our word vectors. So we have here 500 times 100,000. So all of a sudden, you have way, way more parameters than you previously did. And so, like you said, overfitting is very likely. All right, now overfitting is one of the many problems with this, and here I'll show you an example of the very simple word vector example of what this could look like. Let's assume we're trying to train a simple logistic regression classifier on movie review sentiment. And in the training data, we have the words TV and telly. Let's say it's a British data set. And in the testing data that we don't see during training, we have the word television. Originally, we would hope from training our great word vectors that TV, telly, and television are all close by in the vector space. And again, usually those will be 200-dimensional. Nothing will ever in real life be two-dimensional. But let's see what this would mean, what this means when we say we update the word vectors and we basically include them in our updatable theta vector. So what happens now when we train the word vectors? What do you think would happen intuitively when you start propagating TV and telly, and you might say they are negative, for instance? Well, they will start moving around. And the words that we also had pre-trained word vectors for, but that did not appear in our new supervised training corpus, they will stay where they are. So TV and telly might all of a sudden move over here because we keep projecting into them, you're negative. We're going to try to make it easier for the model to predict that you're negative. And maybe it'll be easier for the model to push them all into one specific area of the high-dimensional vector space to create a very simple decision boundary. So here we had in the training data TV and telly. Now those two might move over here, and in the testing data, television will stay where it is, right? And in general, because we only saw the word television in the test data set. Now, of course, when we try to classify the words, we will misclassify television if we see it at test time only, right? And that's not ideal. So we lose a lot of the power of the unsupervised word vectors if we update them on a very, very small data set. In fact, I have a fun visualization I might try to pull up. Where did it go? So this is a fun visualization of word vectors after you train them with sentiment. So here we again projected down high-dimensional word vectors into 2 dimensions. And after you train them on just sentiment analysis, so very simple sort of positive, negative task, what we color them here in is basically the probability of being positive. So the more blue the vectors are, the more negative they are, and the more red they are, the more positive these vectors would be by themselves if you were to classify this model. And if you go in this part of the space, and again, these are just the two first principal components of the space, you see that stupid, bland, thin, waste, awful are all pretty negative words, and they cluster together. So whatever we initialize them with doesn't matter anymore. They lost all this beautiful, king minus man plus woman stuff, and now all their vectors are capturing is whether they're positive or negative. And so we see here in the space mildly, mediocre, generic, all negative words, all coming together, but it doesn't really matter whether they're nouns, like it's an episode, or awful, which is an adjective, right? They're all just semantically and mostly sentimentally close together. And then as we move through the space, we get to sort of the middle part of the vector space, where you just have a bunch of very sort of neutral words, personal, classic, debut, effects, visual, and so on. And then as we go further and higher up in the space, we see more positive words. So for instance, cool and warm are close together, right? Which is, again, semantically maybe not ideal for some other modalities or some other kinds of tasks, but for sentiment, these are both positive. So this is basically the intuition of this very simple example, but in real life. On a larger data set, of course, we train them again in 50 dimensions, and just for visualization we projected them down. All right, so the main take-home message here is that if you have a very small training data set, you never want to update your word vectors, because you will just overfit to that data set. However, if you have a very large data set, it often works better to also train the word vectors for the specific task that you have. So for instance, if you train a machine translation model and you have many gigabytes of training data, it's fine. In fact, at some point, if your data set is large enough, you don't even need to do any of the interesting word vector initialization stuff that we talked about in the previous lectures, word2vec and glove and so on. You can just train on the tasks that you have, and that's it. So, but that you need very large data sets for that. Generally, if you have medium-sized data sets, and again, this also depends, like what is medium, small, and large? It kind of depends on your task. If you have just a binary classification problem, you might get away with a couple of thousand examples. If you have something like machine translation, where your output space is a sequence of words, of thousands of different words in another language, you may need a lot more training data.
Thousands of examples per word?
So in thousands of examples for a simple classification problem, where you have 2 or 3 classes, you have a couple of thousand examples per class. For machine translation, you want to have many hundreds of megabytes, ideally gigabytes of training data. Nobody really has like a how often does each word appear kind of statistic, because you know that you have a very sort of power law distribution of words, and some words will never just, even in a corpus of billions of words, some words will only appear a couple dozen times or less. All right, are there any questions on training word vectors? Cool. All right. So I think in a week or two, you'll all have trained your own word vectors, and this will become second nature. All right. Now, a quick side note on word vector notation, because throughout this class, and as you start reading actual papers in research, you'll see lots of different notations and nomenclature for word vectors. We sometimes use the word vectors, but others use word embeddings. Sometimes we use word representations or word vector representations. They're all basically the same thing. And sometimes we call the final matrix L for a lookup table. Sometimes we call it X. In many cases, you'll see very quickly, what dimensionality it is, and then you'll understand what is meant. Now, when I read my very first deep learning papers, they said, and then we take derivatives, and they just had a lookup table and a hash. And I'm like, how do you take derivative of a hash? This doesn't make any sense. And so intuitively, mathematically, the way you can think of taking out a specific vector from this matrix in order to then initialize some kind of follow-up model with it is that you can essentially left multiply a very large one-hot vector E with this L matrix. So imagine you want to get the X vector, the word vector, out at the location, let's say 2, then you basically take this very large L matrix and you have a very high dimensional one-hot vector E that is basically 0, 1, and then hundreds of thousands of zeros, and you multiply these two together, you have a D by V large lookup table or embedding matrix times this V by 1 vector, and you get back a D by 1 vector, and that's exactly the word vector at the second location of that index. And of course, you're never actually going to want to multiply this very, very sparse matrix with this very large, the very sparse vector with this very large dense matrix. But intuitively, if you try to think of the derivatives and you work through the problem set, you can think of it that way. Yeah?
Quick real-world question. Has someone released like pre-trained word vectors? Are those available?
Yes, that's a great question. So the question is, and so I'm going to repeat them for the videos, have people released these? And the absolute answer is yes. A lot of them have been released. So for instance, if you go to Glove project from Stanford CS, you can download the vectors that have been trained on different data sets. Also, again, understanding that word vectors are very different depending on what they've been trained on. So here you have some Common Crawl trained word vectors with 840 billion tokens, which is not something you're ever going to want to do by yourself. So it's a phenomenal resource. It's also, just to download them, I think in a zipped up format, it's 2 gigabytes. So it's rarely that you ever want to use the entirety of those word vectors. Yeah.
Which one of these should we use?
The best one is the Common Crawl one. We saw in last lecture, in the terms of performance of various intrinsic and extrinsic measures, the larger the better. But when you download this file and you look at it, you'll observe that the last couple of 100,000, so in total this is 2.2 million different word vectors, and each one is 300 dimensional. And this again comes, like these choices came from very carefully looking at the graphs and observing performance for these different hyperparameters. What you'll observe is that the last couple 100,000 are basically different numbers, like 0.001, 0.35, 0.67. Like they all have their own word vector, which is really kind of silly. You don't need all those word vectors. It still helped, because sometimes you may have 0.1 dash debit or credit or something, and then if you see that one again, it might help you a little bit. But you basically have very much diminishing returns from taking the entirety of that word vector. Now, sometimes what you can also do is you can actually run your own PCA. If you say 300 dimensional is great, I want to use the Common Crawl ones, you just take the first 200,000 most frequent ones, and then you say, well, 300 dimensional is still too much. What you can then do is run PCA and only take the first 100 or so.
So they're in order in that file?
They're just ordered by frequency, I think. So but that's a very useful order. Yeah.
So it says 2.2 million vocabulary. So
That's right.
The number of words. And what's then 840 billion tokens? Is that what's token?
So the question was, the 2.2 million is the number of words, the size of your vocabulary. The 840 billion tokens, a token is basically just an instance of a word. And 840 billion tokens is basically the size of your training data set. So yeah, the corpus on which you train the word vectors.
Does it make sense to update your vectors if your data set isn't as big as these?
Yes. So rarely ever will you have a data set ever that is that big. Usually you're lucky if you have millions of tokens in your data set. And once you have a couple million, you definitely want to update your word vectors. Yeah. Though, whenever you're not certain, the best answer, if you think, oh man, I wish I had a professor who gives me advice on my project, and I have the following type of question. I wonder if I should do X or Y, because I don't know which one is better. The default answer that is always correct is to do both, and let the data decide. Look at your test data and let the test data decide which is the better one. Because even the person with the most intuition, they have seen 50 different projects and almost never did it work, but maybe you're the one exception. So you can never go wrong by running the experiment, making the choice that you had in your head by yourself, and evaluating, again, on a development test split. Don't ever run it on the final test data, because then you just start overfitting to that. But that will always be a good answer. All right, those were great questions. Yes?
When you said pre-trained over there, do you mean that you have sentiment analysis that start pre-trained it, or you have what is the why basically?
Oh, great question. So the question is, what do I mean by pre-training? Usually when I say pre-training, I will mean that we use Word2Vec or Glove to initialize these word vectors. Later on, you can start towards the end of the class, we'll get to transfer learning, where pre-training might be you train on sentiment and then you try to predict different emotional classes that aren't just positive, negative, but might be happy, sad, ecstatic, and things like that. And then you might pre-train on an actual supervised task. But in most cases, pre-train just means unsupervised Word2Vec, Glove style training. Cool. All right, so now word vectors, great, useful first step, but rarely ever do we use word vectors just by themselves. They're the first step towards training some real system. So let's get to window classification, which is the simplest of the useful deep learning models. Basically, we're trying to classify rarely ever a single word by itself in complete, independent of the context. Most words appear not in isolation, but in some linguistic context. That context could be images, but in most cases for this class, it'll just be the other words around it. And it's incredibly useful to actually consider that kind of example. So for instance, here are a couple of fun examples where really you have to have the context to understand and even classify something as simple as a single word. So for instance, there are auto antonyms, words that mean their opposite as well as their default meaning. So to sanction, for instance, can mean to permit or to punish, right? Or to seed can mean to place seeds or to remove seeds. And you'll have lots of those examples in English. And of course, just there are other simple words, so even ambiguous named entities. So Paris could be the Paris Hilton or the Paris of France. Right? Or Hathaway could be Berkshire Hathaway or Anne Hathaway. So it might be an organization, it might be a person. All of these are very, ambiguous, and we only know what they really are in context. So let's look at a word in context by essentially just considering it together with its neighboring words. And this model will be one that you'll implement, and it's actually the first reasonable one. Even for your projects, this might be the first that actually is a reasonable baseline to implement. For instance, if you wanted to implement your own named entity recognition algorithm, this is one of the most basic, simple Lego blocks that you can use. So there are lots of different possibilities for classifying a word in its context. One would be you average all the words in a window, but that loses the position, and you might want to know whether the or driving to appears before or after a specific word, because if you're driving to X and you can see all the movement to X kinds of windows will probably make X a location. Right? So you want to have a model that captures that. And so the simplest one that we'll look at today is to just train a simple softmax classifier by assigning a label to the center word, which is again not required. You could have the word that you want to predict as the last word, but for most of this lecture, next lecture, we'll just assume we try to classify the center word of a window. And what we'll do to define our features is simply concatenating the word vectors of all the words that are around the word we're trying to classify. So let's say here, for instance, we're trying to classify Paris in the context of this sentence. So maybe I visited all the museums in Paris, or I think all the museums in Paris are amazing. And now we're trying to classify this word, and what we'll do is basically just take the vector of museums, the vector of in Paris are an amazing, and we concatenate them into one long column vector. And here this looks like a row vector, so I'll make it very explicit. The default for all our vectors will be that they're column vectors, which will be important for all our dimensionality checking and the equations that are coming up. Okay, so depending on our window size, we have a differently sized feature vector x. And those will be exactly the x's that we defined in the very beginning for classification. And y here could be, is this a location or not? Could also be y1 equals its location, y2 is it's a person, y3 it's an organization, and y4 is it's none of the above. That's a very common set of tags or classes for named entity recognition. Okay, so if all of our word vectors are d-dimensional, then, and we have, let's say, a window size of 2 to the left, 2 to the right, we'll have a 5D dimensional column vector. And now we can basically go through our standard logistic regression. X here, each x is the x of our window. We concatenate the word vectors, and we can use the exact same definition of a softmax classifier or logistic regression or cross entropy. Those three are also all synonymous. I usually stick to the softmax classifier in this lecture, but we basically can take the standard softmax classifier and we basically predict here some model output probability with this equation. And we'll update this by taking derivatives of the cross entropy error, and we've basically done most of those in the previous lecture, and in the problem set you'll extend this here to the softmax. But it's going to be very intuitively here, right? You just take the derivative of the log, you apply the chain rule, take the derivative of the inside, and so on. So now the question is, how do you update the word vectors, right? The default here would be we just update W. And the short answer is, well, we just take derivatives as before, but we apply the chain rule again. We don't just go to the W when we take derivatives, but we go one step further. And that's one of the things you'll have to do in problem set 1. And so I want to basically give you now a couple of tools to make this easier for you as you have a complex, well, it's not quite complex, but it's the first sort of most important Lego piece, how to take derivatives of word vectors as there are layers in front of it. So some people might say this simple model where we have a softmax layer on top of word vectors is already a 2-layer neural network. It's not really. You could also say it's not really a single neural network layer, but softmax is considered 1 layer, and the word vectors could be considered another layer too. So let's go over a couple of tools, and those won't be just useful for deriving word vectors, but for all the derivations that you have to do in the midterm, in the problem sets 1, 2, 3, and so on. So step 1, very carefully define all your variables. So let's do this for this exact problem. We just have a softmax here, and we basically want to derive derivatives for the W matrix and all the word vectors x that we see in a specific window. Is the goal clear? Right, mostly nodding. Cool. All right, so let's define our variables. Y hat is the softmax probability output vector. Just this one right here. If we do a subindex of that, then we mean we have the yth class. So just one element of that vector. T will be the target probability distribution. Again, this will be all zeros except for the ground truth class y, where it's 1. And then f, or f of x, is basically just defined as a simple matrix vector product, where we have here a number of rows equals c, number of columns. Actually, let me ask you this question. What do you think is the number of columns for W if we have d-dimensional word vectors and we have a total window size of 10? That's right, 10D, great. All right, whenever we subindex f here, then again we'll take that subindex element of this vector f. All right, this can be a little hard if you haven't taken derivatives for a long time, so we'll go through a couple of tips now. All right, so let's say in our case here we had dimensionality of, or window size of 5. So we have 2 words to the left, 2 words to the right, trying to classify the center word x. And each of them is represented as a d-dimensional vector. And the first thing is not just define your variables, but also carefully keep track of their dimensionality. Because whenever you have any multiplication in your derivations, and you already know just from understanding what matrices you can multiply with other matrices or vectors, and they don't actually are proper multiplications. Let's say you try to multiply x times w, and x is a 5D vector, and w here is a c by 5D. So you have x on the left side, you already know that this is not a proper multiplication, and you already know you made a mistake. And once you implement this in code, it will also nicely throw an error. All right, now step 2, know that chain rule. Don't forget which variables depend on what. So if we have x here, for instance, and you want to basically take the softmax of fy of x here, the yth element of this, make sure you sum over all the classes, and make sure you know that your x is actually in fc of x. So sometimes we'll just write this whole vector as its own variable, but make sure you understand that the variable, this vector actually dependent on a specific other variable. So you can write it as a function also. Now for the softmax part of the derivative, you want to first take the derivative with respect to fc, which is the class that you might want to actually predict, the correct class. And then you can take the derivatives with respect to fc when c is not equal to y, all the other incorrect classes. And some of this might not be as intuitive until you actually go through the steps, and you can refer then to the lecture slides when you go through it. All right, tip number 4. When you take derivatives with respect to one element of your vector f, for instance, try to see if you can create the gradient, the final result in the end, by looking at all the partial derivatives. So for instance, you will notice if you just take all the classes that aren't true, so let's say y here is the true class, and 1 to c with y not equals this exact y, all the wrong classes, then you may basically put this together, and then you see a larger structure, and then you can write this overall as a vector. And this is something that's very important to later not go insane as you're as you're trying to implement this. You basically want to define every time you have something where you have all the partial derivatives and you can concatenate them in a vector, you want to put that into some vector notation. So maybe you can see this being your derivative, and now this doesn't maybe intuitively look like a vector, but then you can see, well, if I just subtract always something on this side, which is 0, then I can write this whole thing in terms of a vector subtraction. So here, for instance, y hat will be our predicted probabilities, and t will be our target. And we'll subtract t. This is basically our target probability distribution, which happens to be exactly one of the things that we defined in our notation in the beginning. And we'll define this as delta, and we'll become good friends with delta in the next couple of slides or lectures. All right, now we're almost at the end. So tip number 6, when you start with the chain rule, first you can write out explicit sums and then look at all the partial derivatives to get a good sense of what's going on. So for instance, as you write down this chain rule, you will at some point hit this kind of sum, and that's very intuitive. You'll have some delta, and don't worry if you don't understand how we got there, but you'll have some delta times the transpose of your softmax matrix. And it's very intuitive what's happening here for each of the classes. But in the end, and this is kind of a skill that you'll develop in this class, you can see, well, if I multiply each of these and I keep summing them up, then maybe what I can do is I can actually combine all of this in one large matrix notation. And again, here it's very important to know that you have the right dimensionality, so you always have to keep track of your dimensionality. It's very quick to subtract points if we see any multiplication ever that isn't even a proper matrix multiplication because the dimensionalities don't add up and don't make sense. So here, you can basically, will eventually see that the derivative with respect to x will be w transpose times delta. And again, if some things are not clear, write it all out in the full sum and then try to backtrack to see if you get to the matrix notation that way. So now, to wake you back up, what's the dimensionality of the window vector gradient? So if we have here x having been the vector of all the word vectors that were concatenated, and we're trying to classify the center word. So intuitively, when we have our gradient of the objective function with respect to this vector, we want to update that vector. So what does that mean for the gradient? Yeah?
If it was, well, if you have 5 words, it would be 5.
That's correct. That's exactly right. So if x is the entire window and we have 5 d-dimensional word vectors, then the derivative with respect to x has to have the same dimensionality, right? We're always going to update theta new equals theta old minus the step size times the gradient of that theta. So if the theta is the current word vectors, then that's the exact update. So that is another sanity check. In the end, after all your matrix multiplications, if the final result doesn't have the same dimensionality as what you're trying to update, you've made a mistake as well. All right. So the gradient that arrives at and updates the word vectors can, in the end, be simply split up for each of the word vectors. So this is not really that intuitive, but, well, it's very intuitive, but you might not sort of derive at it by yourself. So I want to make this very, very explicit. So generally, we'll get some update delta for the entire window. And as we just said, this derivative will be 5-dimensional, but we have actually 5 separate vectors in here. And intuitively, you basically have an error message that arrives from your gradients at each of these vectors. And what we can do to update the whole one is basically just split them all up at exactly the dimensionality. So this will be essentially 5 separate d-dimensional vector updates. And then intuitively, as you update this, you will find what is the actual ID of the museum's vector in your final lookup table or embedding matrix. You find that ID, let's say museums is the 80,000th word, then you look at the 80,000th column and you update that column with this derivative. Yeah?
So what happens if you have multiple of the same word in the same window? So like museums in Paris and France?
That's a great question. What happens if you have the same vector, the same word in the same window multiple times? Well, it's just the same thing. You have here delta of your window, and museums happens here and here. And in the end, you look up the ID and you add both of those derivatives to that ID in your lookup table.
So we just apply to possible.
Yeah. So these are all the very basic applications, and again, usually I know that I will bore 1/3, I'm a little too fast for 1/3, and for 1/3 of the class it's just the right speed. Depending on which one you're at, feel free to come to office hours that we started this week. All right, so now this will again push the word vectors into areas in a way that it will be helpful to determine what are the named entities for the center word. And what intuitively this model can already capture is that when you see the word in, for instance, as the word just before the center word, you already know that this is indicative to be a location, for instance. So these are the simple things that this can now figure out. And if you have word vectors that are similar to in that you haven't seen during training, then if you had a good initialization of your word vectors, it will generalize better to this than if you just had a word index, right? And that's really the power of these word vectors. The similarity of words will enable us to do downstream tasks better and generalize better to unseen test data. All right, now what's missing for training the full window model, of course, we don't want to just train the word vectors. We also want to train the softmax weights. So the gradient, the final gradient of J with respect to the softmax weights, and then with respect to the entire parameters that we may want to update, theta here will essentially be this. And it will again just concatenate a bunch of column vectors together to get the full update of theta. All right, any questions on the math so far? All right, great. So now a note a little bit on matrix implementations, because we'll tell you roughly how long training should take for your problem set 1 as you implement your first algorithm, but it will widely vary depending on whether you use this trick or not. So for instance, for the softmax function, there are two things that are very expensive in terms of the operations. The first and major one is that we have a large matrix multiplication. And that is basically the major bottleneck of all of deep learning, is you have lots of matrix multiplications. And these W's and X's can get very, very large. So at some point, you may have a 5,000 dimensional vector X and a 5,000 by 5,000 dimensional matrix W here, and that's basically a layer that goes from 5,000 to 5,000. It's going to be very large. And then you also have the exponents, and exponents in the computer are also not that cheap to compute. And so the most important thing for implementations in any higher level language, such as Python, MATLAB, Java, or any of them, is that you want to always avoid, as much as you can, any for loops. So let me walk you through an example, a very, very simple one that's similar to this simple example that we just walked through. So let's say we have here all our word vectors, and instead of concatenating them all into one large matrix and then multiplying them, we did just a for loop. So here are the two implementations. Let's say our W we just initialized randomly, and again we have C number of classes, and let's say we have D is 300 dimensional windows. So let's say, you know, we have gotten this from maybe from some other things, it's just for illustration. And let's say we have 500 windows in total that we want to classify. And generally, and the graders, me and the graders would all appreciate if you also properly define all your terms and your variables this way. Now would end up with some kind of matrix W here for our softmax, a C by D matrix, and we have basically our word vectors, which will just be a bunch of random d-dimensional vectors, and that will basically here be our word vectors as the entire matrix. So let's say we had, for instance, n many different windows, and each of the windows was d-dimensional. Now, if we did a for loop over all the windows that we have, versus we have one very large matrix multiplication where we multiply all the windows in one go, the difference is huge. So here, when you have basically this implemented as a for loop, it'll take 600 microseconds, and if you had it in one large matrix multiplication, it would only be 50 microseconds. Right? So, and right now these are all small numbers, but even in your projects, you'll have tens of thousands of windows, and you want to go over this matrix many, many times, and this could be the difference between 12 days or 1 day, right? And that will be the difference between you submitting the project on time versus you having no results to show, right? So very, very important. Yeah.
On the topic of runtime performance, I noticed that NumPy doesn't by default do parallel matrix multiply. Is there a way, like a clean and cheap way to get it to do that, or no?
So it's still more efficient even if it just uses one CPU, but you're right, it's non-trivial to make Python do proper multi-CPU even implementations. It's super hacky and hard to make it work, and that's one of the main reasons we went through all the work or are going to go through the work of updating the problem set 2 and 3 to use nicer frameworks that will do that for you. In fact, they will not just do it for CPUs, but also potentially for GPUs, and that will help you immensely if you have a GPU.
So we can't like give it an argument and say, please use all my CPUs?
Unfortunately not. There's no simple way to make Python nicely use with NumPy all the cores that you have. But this was also not done, like this was just done with simple NumPy things, and it still has that speed advantage. So just from the overhead and the efficient matrix multiplication, it already helps a lot. Are there any questions about this code? Cool. All right. So matrices are awesome. Should always do this. Also, the time it quick hack if you are in an IPython notebook is super helpful. Sometimes you think you have two vectorized implementations and you're not quite sure which one is more efficient. Again, there's always a simple way. You just try both and you time it, literally, and then you can know which one was faster. So the speed testing of your code is going to be very useful. Otherwise, you're just going to sit in front of the computer for a long time and keep checking your results. All right, now I mentioned softmax, and softmax is the first simple thing. But if we have the word vectors and we fix the word vectors, it's not very powerful because it's only going to ever give us a linear decision boundary. And sometimes the linear decision boundary is actually not so bad. If you have very high dimensional input data and you don't have that much training data, then forcing your function to only be linear might be actually some way of regularizing your model, like keep the model very simple. But as you have more data, and that's exactly the regime where deep learning will be so useful, it is very limiting. So let's say, for instance, here, you started with simple softmax, or again, logistic regression, just a synonym, and you have training data in green in one class and red in another class. And this is kind of lame, right? We basically, with a linear decision boundary, we could never get to classify these points correctly. And again, if you have very little data, you might not want to because they might just be outliers and you would overfit. But if you have lots of data and it's clear that the data and the ground truths or the real manifold that your data lies in is just not linear like that, then it would be nicer if we could actually have a decision boundary that looks like this. And that's when we'll use neural networks. Because neural networks will enable us to give us arbitrarily complex decision boundaries of that nature. They're so powerful that they will very quickly overfit. So here in this case, for instance, we have so few training examples that this is clearly an overfit example. But as you have more and more, it'll be actually very powerful to have that. So now, since we've defined and very carefully analyzed and you'll derive all the logistic regression derivatives and so on, we can use that notation to define neural networks, and we'll really start building. You can really see this as a Lego block. And yes, the first couple of Lego blocks are not that exciting for the class, but you can start very quickly build very cool things once you know them very well. So let's demystify neural networks a little bit and just define the terminology for neural nets. So basically, there's lots of terminological baggage, but it's kind of true for every machine learning model. So once you understood the softmax, it'll be very easy to understand what a single neuron does, and then we just kind of put them all together with very deep neural networks. So single neuron will often say it has some inputs, and sometimes we also define it to have a bias unit that basically also is sometimes referred to as the intercept term. Then we will have an activation function and an output. So let's look at one very simple definition of how we can define a single neural network unit or single neuron. And again, neurons sort of in scare quotes. Real neurons in the brain are very, very different, much more complex. There's a very simplified model. And in some ways, really, we could also just call it a binary logistic regression unit. This doesn't sound quite as cool as a neuron, but they're also synonymous. So here is one way of defining this. We basically have our h here, which is the full output. H of x is the output of one neuron when it gets as input a vector x. And we have here a simple inner product with with a vector, in this case for now, a vector w. And because the default for our vectors are always that they're column vectors, we'll say here we transpose this, so it's a row vector, so we have a row vector times a column vector. And then b here is our always on feature. And again, other terminology for that is the class prior or the bias term. And I'll personally use bias term most of the time. So b here in our case would just be a single number for a single neuron. Now f, I mentioned before, we could have here our sigmoid function. That's the simplest one. It's not one that we're going to use a whole lot, but it is going to be used even in very fancy models later on. So basically, f of z just basically maps any real number to be between 0 and 1. As a squashing function is also what we sometimes call it. All right, that's it. That's a neuron. That's the simplest small Lego piece. And now we can basically say, well, we have some input. These could be our word vectors that we already know. And we plug them into a bunch of these logistic regression functions or neurons. And maybe we'll do that a couple of times. And we have different neurons all on the same input. And all of them have their own bias term here. And maybe we can do that again and again. So here it's not really clear what we're trying to predict yet. So maybe what we would do is instead of giving those directly as like a single output, so here the model we've walked over before was where we tried to classify this unit, for instance, is this a part of a named entity location or not, right? And we could have had this neuron here also define, is this a person or not? And we have different binary classifiers on the same window input that we defined before. But the main idea of deep learning will be that we won't define explicitly what these intermediate logistic regression units will do, but we'll actually have another logistic regression unit that sits on top of the output of those. And now it's basically the loss function that we have on this layer that will determine what these so-called hidden or intermediate layers and variables should capture, in order to make the final prediction at this layer to be very accurate. And that's basically it. That is we took this simple Lego block of a logistic regression unit, we can put it together in sequences, and then we can follow them up with multiple other logistic regression units. We plug them all together, and that's the definition of a deep neural network. And that is going to be the major focus for the next couple of lectures, really understanding all the notation and all the computation and learning of these kinds of architectures. Yeah?
Is the multi-layer neural network the same as multi-layer logistic regression then?
Yeah, you could say that. So multi-layer logistic regression, it kind of depends on how you define it, but I would say in the end, up here, you have a logistic regression layer, or a softmax layer. And if you say it has multiple layers before it, then that would define a deep neural network. Or a multi-layer perceptron is another word that you sometimes see in the literature. Yeah.
What is the question neuron?
Sorry, say again?
Plus one neuron, additional neuron, the added layer.
This one here? So this is the bias term. So in order to have, we'll get to that in a little bit, in order to have a bias for each of the neurons that we have in intermediate layers, sometimes people write this as a +1 here. It kind of is just notation for visualization. But basically it will give us a bias term that is independent of the input. And sometimes you might want to say, this neuron, maybe it's just never that useful, so the bias term is very largely negative in magnitude, which will then push because of our activation function here, if B is very large and negative, it will go down here, and then no matter what the input is, that neuron will never be on. And maybe some neurons for later layers, it'll be helpful that they're always on, and then if your B term is very large, then no matter what the input is, you'll always be somewhere over there. Yeah.
In general, how do you decide how many layers you have?
Ooh, that's a tough question. How do we usually decide how many layers we'll have? There's some intuition, there's some basically experience for different kinds of problems, how many layers are useful. The best answer is the one of try them all and look at your dev test performance. Try 1, 2, 3, 4, 5, and usually if after 3 to 4 you don't see any there's improvements, it stops making sense to add another one. But we'll get to sort of when does it make sense to have how many layers. In many cases 1 or 2 is actually the right answer and it's already enough. Yeah.
So to follow up on his question, it seems like word to vec has 2 layers because you have the logistic hidden layer and then the softmax output. Is there a reason why that was like decided upon? Like everybody uses that?
So it was decided. So one, it's technically only at most a single layer, because you have the word vectors, which are linear, and you have one sigmoid on these word vectors, right? The inner product. So remember, in the objective function, you had sigmoid of your center word times the outside word. And that was all. And then you had another part where you had center word and a bunch of random other words.
So you still had softmax loss, right?
No, that was the final loss function. You'll see it once you implement it, but that was, you just take the derivative of the sigmoid. There's no other thing on top of that. And so it is really the least deep model that has ever been called deep in deep learning.
So then it's basically just a linear model, which is why it's only 1 layer.
That's right.
I wanted to have nonlinearities.
That's right. It basically only has one output with one sigmoid. And usually what we define as one proper layer is exactly this, which is a linear layer plus some nonlinearity applied to all the elements. So let's define this very carefully. So one neuron, A1 here, its output will be computed by basically this simple sum, where we just wrote essentially out what the inner product here is between the first row of the matrix W, which defines that entire layer, and the first row times the input is basically plus the bias term is the output of the first neuron. And the second row is just the second row of W plus the bias term. And that's how we can essentially, we can put this all together in matrix notation and then just write Z equals WX plus B. And so the number of rows of W is the number of layers that we happen to have here. Sorry, the number of neurons that we have in this layer is the number of rows in W. And the number of columns is basically just the number of the dimensionality of the input here, X. And whenever we write F here, now very important, in a couple of slides before, we called F a vector. From now on, F will be a function. It will be our nonlinearity, like the sigmoid. And the sigmoid function is, of course, only defined for a single number. And so whenever we write F of a vector, what we mean is we apply this element-wise. So F of Z1, Z2, Z3, the vector, will just be F of Z1, comma, F of Z2, and so on. Yeah?
So here X1, X2, X3, they are basically the different dimensions of the input. So it's a given window, and we're taking the first and third dimension.
That's correct. So the question is, what is our X here? You could, for instance, see X as the window that we have, and each word, let's say the window is only size of 3, so there are 3 word vectors, and each word vector is only 1 dimension. Simplest kind of word vector you can have, just a single number. Now that would then give us exactly this kind of input. So each X here is just a single number. So this is abstractly defined, right? It could also be a single vector that has 3 dimensions, and you just classify one word vector here in isolation.
So it basically is a real number. It's not capped between 0 and 1, right?
That's correct. Yeah, that's a good question. Is X a real number? X could be anything. X in many cases is a real number, but, and we'll get to that very soon when we look at tips and tricks on how to not mess up training these models, you do want to make sure that X isn't gigantically variant. So because if, for instance, X here sometimes is 1,000,000, then whatever comes out here and you multiply and one of your elements of X here is 1,000,000, then all of a sudden this W, no matter what it is, small random number, large random number, will dominate everything. And then very likely if you multiply this X element with 1,000,000 and W here is positive, then this A1 unit will just be always on, right? Because you will then be very quickly right here, somewhere way out here, for your sigmoid activation.
So this only affects the first layer, not the ones after that?
That's correct. It will only affect the first layer. So this is just the definition of a single layer, and so all of what I've just described will only be true for that first layer. Yeah?
But even if that one neuron has really high activation from the input, could it learn a bias to sort of counteract that?
It could, but we'll get to that very soon. But what happens if you try to optimize a function and you're stuck right here? What's the gradient going to look like if you're up here? That's right. It's basically flat. And so it's 0. So you're already stuck in a local optimum. And that's why making sure your inputs are in a specific window and your weights are such that you start somewhere here and not somewhere way out here or way back here of the sigmoid is going to be important. We'll get to all of that as we learn to implement these from scratch. All right, so now nonlinearities, F, why are they needed? So you might say, well, why don't we get rid of the nonlinearities and we just have multiple W matrices? Well, that's going to be completely useless because the nonlinearities are really what enables deep neural networks to learn much more complex decision boundaries that look like this instead of just linear decision boundaries like this. If we had no nonlinearity and we just had added a bunch of separate W matrices, well, you could just basically multiply these together first and you would end up again with just a single linear layer. So it's really these nonlinearities that make neural networks so powerful. So to give you an intuition, let's say we had, and we'll get to this model in very soon, but let's say you had a very simple one-dimensional input here, and you had different numbers of hidden layers, a single layer only, and you tried to have a simple linear regression output here. Now, if you had one hidden neuron, this would be how you could fit these points. If you had 3 hidden units, you could fit this function, and if you have 10 hidden units, you can basically completely overfit this function, and your regression algorithm will be very, very overfit to this specific data set. So this is kind of a regression example, and this is a classification example where we have decision boundaries and decision regions. And we'll usually want to have a couple of layers that are variable sized in their depth. And another way of thinking about this is that deep neural nets are really just general function approximators. You have any kind of function you try to approximate, it will be defined over some kind of n-dimensional input. In this case, for instance, just a simple 2-dimensional input, and you want to learn a function that basically maps any point in that input to a specific output class. And that's the magic of deep learning. They're general function approximators. They just happen to be very, very powerful as we add more and more of these layers to them. All right, now let's actually look at a more powerful window classifier that we'll be using in practice, and that actually started in 2008. One of the most exciting papers that have come out in deep learning in a very long time until then by Colbert and Weston. So let's say we revisit again our window classifier, but now instead of taking the input vectors x and directly giving them to a softmax, we will first give them as input to a hidden layer, a hidden neural network layer, and then to a softmax. So let's define what this will look like. So we have here x, which is again just a concatenated, it's not so gross. We had a single layer, neural net here that we'll define in the standard notation where we have a linear layer followed by a nonlinearity. So we have here our concatenated word vectors in X, and we plug them through this matrix multiplication straightforward to now have an element-wise nonlinearity. And now the neural activations that we often call A basically can be used to compute some other function, right? And now this could be the softmax, which we used before, but it could also be just a very simple unnormalized score. And we're going to want to say that maybe the score for X should be very high if the center word in the window that is defined by X is a location, for instance. And we'll soon get to why we might want to use just a score instead of the softmax. But intuitively, we could also use the softmax. Now, in order to compute that window score with a, again, some people might call this a 3-layer neural network, others might just call it a 1 hidden layer neural network, will be as follows. So we take here our window, we concatenate the word vectors. Let's assume, for instance, each of the word vectors is 4-dimensional, and we have 5 of them that we concatenate. Now, the first layer will be, again, a linear matrix vector product plus the bias term, matrix addition, simply element-wise nonlinearity, and then we'll compute a score. And that score is just U transposed times A, which is just a simple inner product. So we could now define the entire computation as basically this way. It's U transpose times F of WX plus B. And that's the definition of our first useful 3-layer neural network or 1-layer hidden neural network. And again, this one is the hidden layer. Nobody quite knows what these should be learning. But you can also say, well, our word vectors are a layer, this is a hidden layer, and this is the output layer. So you might call it a 3-layer neural network. And this might compute a score here for museums and pairs are amazing, and we might want to say this score here should be very large if the center word is a location. And these should be very intuitive in terms of dimensions. So our X vector here, we had 4-dimensional word vectors, and we have 5 of them concatenated, so we have a column vector of 20 by 1. That means that W, if we want to have, for instance, 8 hidden neurons in our first hidden layer, should be an 8 times 20-dimensional matrix, and then U again is an 8 by 1 output layer. And in the next lecture, we'll actually learn how to train this kind of simple window-based neural network, and then we'll take deeper derivatives, which will eventually lead us to the powerful algorithm of backpropagation. Backpropagation will eventually just be applying the chain rule and being smart about it. But because it's non-trivial to actually derive it in its full glory, eventually people gave it a name. And really after that, we have all the basic tools. We'll stop going through nitty-gritty derivatives with lots of sub-indices. We can say, all right, we understand now what a layer is. Now we can put them together and we'll learn very powerful, cool functions. Thanks.
When in diagram of the neuron nets that you drew with the axis, x-axis up to like some xn being fed to